The last section that we're going to learn about in Chapter 5 is about bond enthalpy. And bond enthalpy is associated with the energy of breaking 1 mole of a bond when it's in the gaseous phase. Bond enthalpy is always a positive value because to break a bond, you have to put energy into it to pull it apart. And so we always have a positive value for this. Energy, though, is always released when we form a bond. It's just kind of like the opposite. And so that's where we'll see in our calculation a negative sign when we subtract due to the formation dealing with energy getting released or being exothermic. The higher the bond enthalpy, the stronger the bond. So double bonds will have a larger value than single bonds. Bonds that are stronger, maybe they're shorter, they're going to have a bigger value because their shorter bonds are also stronger. And so we'll see that relationship when we look at these values. So we're going to basically take all of the bonds that we form, so all the bonds made, and we're going to add them together. It's going to be a positive value. And then we're going to take all the bonds that are broken, and again, we're going to get the bond enthalpies, which are positive values, and we're going to subtract it, which is going to make it a negative value. So that when we have bond energies or bond enthalpies, we're going to do this equation, which is the enthalpy of broken, things that got broken, minus the bonds that got formed. And bonds that get broken are in the reactants. And bonds that got formed are the products. So we could see here in this chemical reaction, we have methane and chlorine, and they form a single chlorine bond with the methane, a chloromethane, and then hydrochloric acid or hydrogen chloride. So notice here, between methane and chloromethane, a single bond gets broken. So this bond got broken. So we would add up the energy that takes to break that bond, and then the amount of energy that associated with breaking this bond is also going to be positive. We had to break that, the chlorine-chlorine bond. And then we're going to rearrange and form these new bonds. So the energy associated with that bond and this new bond are going to be in there, and we're going to subtract them, making it a negative value. So when we do this, we're going to need to write Lewis structures, draw the Lewis structures for each of these, and we also want to keep in mind the coefficients. So in here we have 2 moles of ethane and 7 moles of oxygen reacting to form 4 moles of carbon dioxide and 6 moles of water. Oops. So we're going to need the values for each of these bonds, and you can find them in a table. So I will tell them to you as you go, but the thing we're going to do is going to say the enthalpy of this reaction can be associated with the bonds that got broken minus the bonds that get formed. So let's look at who got broken. We can see, I'm going to do it in a green. We can see there were 1, 2, 3, 4, 5, 6 carbon-hydrogen bonds, single bonds that are going to get broken. Because you can actually look at the reactants and products, there's no bonds that are maintained. All of them get broken and you form all new bonds. So we have 6 carbon-hydrogen bonds there, single bonds. We also have a single carbon-carbon bond here, and there's only one of them. And notice though, this whole molecule is going to be multiplied by 2. So I'm actually going to have times 2 and times 2. So we actually have 12 carbon hydrogens and 2 carbon-carbon. And then here with oxygen, we have a single oxygen or a double oxygen-oxygen bond, just one of them though. And so we have 1 oxygen double bond, but we have 7 out front, so times 7. So those are all the ones that got broken. Let's look at the ones that got formed. I'm going to draw them on the right side. We have 2 carbon-oxygen double bonds but there are 4 of these molecules, so times 4. And then we have, I guess I'll do it in green. We have 2 oxygen-hydrogen bonds here. Single bonds. But there are 6 of them, so times by 6. So now what we're going to do is actually look up the values for each of these and plug them in. So we're going to have, just write with black here, so we have 12 times, each carbon hydrogen bond is 413, we could find this in the table, kilojoules. We have 2 carbon-carbon single bonds, and each of those are 348 kilojoules. And then we have 7 oxygen-oxygen double bonds, whoops, and those are 495 kilojoules. So then I can actually add up all of the energy associated with breaking bonds, and it is 9117 kilojoules. So that's how much energy is involved with breaking up those reactants. Now for the products, we're going to have 8 carbon-oxygen double bonds. Those are 799 kilojoules. And 12 hydrogen-oxygen single bonds, and those are 463 kilojoules. So when we add up those, we end up getting a total of 11,948 kilojoules, and that's how much energy gets released when we form. So we're going to do broken minus released, and our delta H of this reaction is going to be negative 2831 kilojoules. All right, so now we have this molecule. This is hydrazine, and we're going to try to calculate the bond enthalpy related to when hydrazine decomposes. So we need to draw the molecule from the Lewis structure. We're going to have the 2 nitrogens connected by 4 hydrogens, just like that. And that goes to make a nitrogen. I just know that nitrogen has a triple bond from seeing it with 2 lone pairs and 2 hydrogens, and that's just a single bond. So then we can calculate here. We can count. First thing is counting. We have our hydrogen-nitrogen single bonds. I don't see any bonds similar from the right to the left, reactants to products. Okay, so I have 4 nitrogen-hydrogen single bonds, no coefficient in front. And then we have 1 nitrogen-nitrogen single bond. Okay, there's my reactants. My bond's getting broken. Then we're going to have 1 triple bond from 2 nitrogens. So 1 nitrogen-nitrogen triple bond. And then a single hydrogen-hydrogen bond, and there's 2 of them from out front. So 2 hydrogen-hydrogen. All right, so then we can calculate all of these, find the numbers from the textbook, from the table. We have 4 of these times 391 kilojoules, and 1 of these, which is 163 kilojoules. So there's our broken. Then we have our nitrogen-nitrogen single bond, or triple bond, there's 1 of them, times 941 kilojoules. So again, triple bond, a lot of energy in there. And then we have 2 hydrogen-hydrogen single is 436 kilojoules. So we could just do this value, add it, minus this value. And when you do that in your calculator, you get negative 86 kilojoules.